It is well known that electricity and magnetism are linked. For example, when an electric current is run through a long wire, the needle of a compass can actually be deflected. This occurs because the flow of electrons produces a circulating magnetic field around the wire, with permanent magnets like the compass needle rotating to align with the field lines. While the field lines around the straight wire do circulate counterclockwise, they have no polarity. If the wire is bent into a closed loop, however, it now has a north and south side. The field lines now originate from north to south like a dipole. Essentially, the loop acts as any other permanent magnet. During our project, we used this fact in order to create trains that have nothing more than batteries, copper coil, and magnets. If a magnet is placed on each terminal of a battery, placing the battery inside the copper coil will complete the circuit. Since the copper coil basically creates loops of current, it acts like an invisible bar magnet between the magnets already on the battery terminals. The upper magnet is pushed, while the lower one is pulled, forcing whatever is in between them to move forward. This system is also known as a homopolar motor, because the direction of neither the current flow nor the magnetic field changes. In order to explore the relationships that work in the battery train, our group devised two experiments. In the first, the effect of the voltage on train performance was determined. 3 batteries, each with a different potential difference, were run through the same copper coil while their velocity was recorded. In the second experiment, the same battery was used, but instead of changing the voltage, only the number of magnets attached to the terminals was adjusted. For each set of trials, a few key items were necessary, such as a 1.5 volt alkaline battery, a 1.2 volt nickel-cadmium battery, a 3 volt lithium battery, 18 gauge copper wire, 8 neodymium magnets, and other tools like a meter stick to record the length of the copper coil, and a timer to measure how long each train takes to cross the coil. For both experiments, the setup process was almost identical. Firstly, the copper wire had to be wrapped into a coil, tightly enough to create a strong magnetic field when a current is run through it. The train was prepared by taking the chosen battery and placing at least one magnet on each end. The north pole of each magnet needed to be in the opposite direction of the other, or else they would be both pushing or both pulling the train and no movement would occur. Both experiments involved measuring the time a given train took to cross the coil. Experiment 1 tested the effect of voltage on train velocity. Each trial tested a battery of different voltage, with the time being recorded for how long each one took to reach the end of the coil. Because velocity equals distance over time, the length of the coil could be divided by the time to find the velocity of each battery. The graph of the data might suggest that voltage is directly proportional to train velocity. At the same time, it should be noted that there is a lack of data, since only 3 different battery voltages were tested, and the resulting velocities were so close to each other that they may be within a margin of error. To ensure the accuracy of the trend that the line of best fit represents, it would be necessary to test a greater range of battery voltages. Experiment 2 involved determining whether a relationship existed between the number of magnets attached to the battery terminal and its velocity through the copper coil. Unlike experiment 1, all 3 trials used the same battery model and voltage. After each trial, 2 more magnets were attached to the battery's positive and negative terminals before recording its time across the coil. The graph of the train velocity as a function of the number of magnets supports a direct proportionality between them. While there may be some inaccuracy in the trend line due to the lack of data, each successive trial saw a fairly significant increase in velocity. Compared to experiment 1, it would appear at least that an increase in magnet count has a greater impact on train speed than simply increasing the voltage.